to give us harmonics. Okay? So pulse inversion harmonics is an imaging technique specifically designed to utilize harmonic reflections. Okay, so as we learned before, harmonics happen naturally, right? Because of the bandwidth and of the nonlinear behavior. Okay, but in this case, the ultrasound machine is making the harmonics. Okay, so with pulse inversion harmonics, 2 pulses are sent down each scan line. Okay, so think of the scan line, okay, like the spoke, right? There's 2 pulses that are sent down that scan line. The first pulse is a normal pulse. The second pulse is an inverted version of the first. Okay, so let's say that we have one pulse that is up this way. We have a second pulse, the opposite. Okay, it's like a it's like a mirror. Okay, they're mirror pulses. Okay, so when they're received, the fundamental frequencies from both waves cancel out. And what's left is the harmonic frequencies because of constructive interference. Okay? Does that make sense? No, I know it doesn't make sense. Okay, it's kind of, it sounds weird, but if you think about it, it's really simple. All right, so we have so we have a scan line, right? We have a scan line. A pulse is sent out that scan line, okay? So let's just say that this is our pulse, okay? Now the machine will send out the inverse of this pulse, which means that it'll be like that, okay? But what lies within the bandwidth of these pulses? Because these are linear behaving pulses, right?
Mm-hmm.
What lies within these linear behavior pulses?
Non-linear?
Huh?
Non-linear?
Non-linear pulses, right? Because of constructive interference. Okay, so let's just say that we have these jagged pulses, non-linear pulses that are within it, okay? So these are traveling, and as these travel, the non-linear pulses constructively interfere, and then these 2 pulses get sent back to the machine, okay? So the machine will use a mathematical equation to cancel out the fundamental frequency from the reflections, and what we're left with is these 2 harmonic frequencies that constructively interfere to make one big harmonic. Okay, so again, pulse inversion, inverse, right? So it sends 2 pulses, one is the inverse of the first. It cancels out the fundamental frequencies, and we're left with the harmonic frequencies that constructively interfere through nonlinear behavior and are more intense than the fundamental frequencies. Okay, because if you remember, we have the natural focus, and then we have the harmonics that lie within, right? And because of our intensity equation, power over area squared, we know that this intensity will be, or sorry, this pulse will be more intense because there is a smaller area, right? More intensity means a clearer image.
So the top example, basically, they become one? Is that what-
Yes, they
Okay.
completely interfere to become one.
Oh, okay.
Okay, So the machine cancels out the fundamental frequencies, and we're left with the harmonic frequencies that combine together to make one intense frequency.
Thank you.
Okay, does everybody grasp this? You sure? This is just one slide. Okay, so again, you see here it's sending out two pulses, right? It's sending out two pulses per scan lane. This is the fundamental frequency, okay? You can see that it's inverse, right? It's inverse. Okay, so just like in constructive interference, when two waves are completely out of phase, they're the exact opposite of each other, right? So they cancel each other out, right? They're completely out of phase, they're the inverse, okay? Well, what's left is this nonlinear harmonic that is not completely out of phase, so it comes together, it joins, it constructively interferes to make a more intense pulse. Okay? Does that make sense?
So the first one's cancel out, and then whatever's left is B, and then
Okay.
goes
So let's not call it the first ones, let's call it the fundamental.
fundamental.
Yes. The fundamental frequency, which is linear behavior, is canceled out, and we're left with the nonlinear behavior harmonics. Okay, so that's pulse inversion harmonics. Now we have power modulation harmonics. Okay, what do you think modulation means, Emily? When you modify something, what do you do?
Oh, you change it?
Change it, okay? So this is exactly what it's doing, okay? So it's changing the intensities, okay? So power modulation harmonics is another imaging technique designed to augment harmonic reflections. It achieves the same goals as pulse inversion harmonics, but it uses different engineering approach. Okay, so it sends two pulses down the scan line, okay, the same. Except that the second pulse is twice the strength of the first one. Okay? The first weaker signal doesn't have enough intensity to create harmonics. However, the second one creates a harmonics. Okay? Now during reception, the first signal and intensity is, or let's call it the fundamental intensity, is canceled out mathematically, and we're left with the harmonics, okay? So during reception, the reflections from the first pulse are doubled and then subtracted from the second reflection. The fundamental waves are canceled and only the harmonics are left. Does that make sense?
No.
No, it doesn't, I know. Alright, I'm turn this back up.
Does this one involve us do math?
No. you just need to understand the concept of the harmonics. The machine does all the math for us. Okay, so again, we have one scan line, right? Okay, 2 pulses are sent. The first pulse is a weak pulse, okay? The fundamental pulse, okay? The second pulse is twice this fundamental pulse, okay? What else is twice the fundamental? The harmonics, right? Okay, so the first one doesn't contain harmonics, okay? Because it doesn't cause the cells to vibrate as much and cause that nonlinear behavior. The second one is already twice this fundamental frequency. So this one creates harmonics, okay? So these travel into the body, and then upon reception, the machine will do a mathematical equation and assign this fundamental value twice the value. It'll assign it twice the value to cancel out the fundamental frequency in the second one, in the second pulse. So what we're left with is the harmonics here. This, to me, sounds very redundant. Okay, but that's the way that the machine does it. Okay, so the first pulse is weak. Okay, it doesn't contain the intensity to create harmonics. The second pulse is twice the frequency, or twice the fundamental value of this one. This one does contain harmonics. Okay, but how do we cancel this fundamental frequency out?
Interference.
Huh? You double this one to cancel this one out, right?
You double the weaker one?
You double the weaker one to make it the same fundamental, and they cancel each other out, and what we're left with is this harmonic frequency. Okay, so what's being changed, or what's being modified, is the power. Power modulation. Okay, power modulation. And what is this one? Pulse inversion. Okay, both of them create what? Harmonics. And why are harmonics beneficial?
Better resolution.
Better resolution because of what?
Less attenuation.
Less attenuation, and they're what? More intense. They're more intense. Okay, remember, they're more intense because they are created within the bandwidth of the fundamental. Okay, less area, same power, more intensity. Okay, what is this one called?
Power modulation.
Power modulation. What is this one called? Pulse inversion, what? Harmonics. And what do they create? Harmonics. Is that good or bad? It's good. Because of what? Less attenuation and better resolution because they are more intense. Okay, that's what you need to take away from this. Yeah? Good? Okay, so here we have examples of power modulation. Does that make sense? Okay. So, let's just say that this is, let's just say that this is a fundamental pulse, right? This one is twice the size of the fundamental, right? Okay, so if we multiply this fundamental times 2, it becomes the same size, right?
Yes.
And they're the same size, and they cancel out because they're they're the same one, right? Okay, so they cancel out, and what we're left is with this guy. Okay? So we're left with the harmonics, because the harmonics live in the bigger pulse. As the fundamentals are canceled out, then we only use the harmonics. Okay, so this is the same thing, okay? So we have a weaker pulse inside of a bigger pulse, okay? We make it bigger, and now they're the same size, we subtract it, and what we're left with is the harmonics. Okay, so again, what causes harmonics? Non-linear behavior. Can you give me an example of non-linear behavior?
The weather.
The weather, okay? The weather is what? Unpredictable, okay? If we could predict the weather, it would be linear, right? Okay, so I want you guys to think of sound moving through a cell, right? If we have this frequency that is very low and causes very little distortion of the cell, what type of behavior do you think this is? Linear behavior, okay? Because this just causes oscillations, okay? Oscillations are predictable, okay? They're predictable. We could use mathematics to predict when there's a compression and a rarefaction, right? Compression, rarefaction. Okay, now, if I have an unpredictable method of distorting this balloon, this cell, what behavior is that? Non-linear, okay? So this is where the nonlinear behavior is created because all cells do not manipulate the same way, right? Okay, how many different tissue types are there as the sound propagates through the body? There's a lot, right? And each of those cells responds a different way, okay? So if they have through transmission through a fluid, but then it hits soft tissue, that hits connective tissue, that hits muscle, and then it bounces back, okay? So all of those fundamental frequencies create harmonics because of that nonlinear behavior, okay? So these harmonics are created by what?
Interference.
Pulse inversion, power modulation, and tissue harmonics are all created by what?
Interference.
Nonlinear behavior in the tissues, right? Yes? Melissa? Yeah? They're created by nonlinear behavior in the tissues. Yes. Okay. Now, we have contrast agents. Okay, so what is contrast? What is it? Well, yes, but like, what does the word contrast mean?
Brighter?
Huh?
Brighter?
No.
Opposite?
Compare.
Comparing, right? Okay, so we can see the contrast between anechoic and echoic, right? The contrast. Okay, so we have contrast agents. Okay, so contrast agents are exactly what you said, Allison. Okay, so contrast is like a dye that they inject to the body that responds different from normal cells, and the machines are able to identify. Okay, has anybody ever done a barium swallow CT? Or a CT with contrast? Okay, yeah, I've got one done too. I've done a bearing contrast CT and I felt like I peed myself. It was crazy. No, warm, like in the genital region.
Yeah, they're like, you're gonna feel like you're peeing yourself, but you're not. And I'm like, what am I on?
Yeah, alright, so do you think that those images look better than a regular CT? Okay, they do look better than a regular CT because it's easier for the CT to identify the contrast than it is to identify the whole tissue, right? Okay, so they go to a specific region, okay? So not only do they use it in X-ray and MRI and CT, but we use it for ultrasound also. Okay, but we inject microbubbles. Okay, what does micro mean?
Very tiny.
Tiny, right? To what size? To the millionth, right? Okay, microbubbles. Okay, so these are really small bubbles. Okay, so they're gases that are encapsulated in a shell. Okay, now what do you think differs, or is the difference between a microbubble and a regular cell? What do you think the benefit is between the two?
Oh, they don't come.
They're predictable?
Huh?
I don't know. They're predictable?
They
I
don't
don't know.
compress.
Oh, they compress
Oh, they do.
faster. Not only do they compress, but they react irregularly. Okay, so the tissue cells within the body are a little bit more, let's call it dense, than the gas bubbles, right? So it takes a little bit more energy to make them react in a nonlinear way. Gas bubbles are very easily distorted, and we can make them act in a nonlinear fashion easier, okay? Just by putting the ultrasound on, okay? So they are injected into the circulation or they are ingested, okay? So you can either drink it or they could apply it to your veins directly, okay? The contrast agents have different acoustic fingerprint than blood or tissue. What is acoustic fingerprint mean?
Would it be like the color?
Like
Would
that.
it be good?
So yeah, so it has a different acoustic property than that of soft tissue or blood. Okay, so the machine knows that it's going through soft tissue, right? It's in the mathematics already. It's already installed. Okay? Now if something is not soft tissue, what does it look like? If it's faster than soft tissue, what does it look like?
If it's faster, you think? And it's what?
No.
Hyper.
Brighter.
Oh.
Hyperechoic, right? If it's slower,
Hypo.
anechoic, right? Yes?
Yes.
Okay, so that's how we can tell the difference between the tissues because of the different propagation speeds within those tissues, right? Now, contrast agents have a completely different mathematical equation, okay? So they're easier to identify, okay? It's like seeing like that one white person in a room full of Mexicans. Right? Everybody has that brother-in-law named Jeff? Okay, so it's that same thing, okay? It's like having a pail full of red M&Ms and there's one blue one. It's easier to identify, right? So if it's easier to identify, that means that the machine works less, which means our image looks better. Okay? So they're designed to create strong reflections that light up blood chambers, vessels, and other anatomic regions. Contrast agents must meet the following 5 requirements. First of all, they must be safe to ingest or to inject. Okay, they must be metabolically inert. What does it mean?
Like The body can break it down.
The body can break it down. Is this good to be broken down really fast?
It must withstand the metal.
Yeah, okay, so it has to. So yes, it has to be absorbed by the body, but it has to be able to withstand the body's metabolism for a certain amount of time. Okay, so metabolically inert and long-lasting, they go hand in hand. Okay, it has to be a strong reflector of ultrasound and small enough to pass through capillaries. Okay, so remember, these microbubbles are made. Okay, they are intentionally made to meet these criteria. Okay, so here's an example of what a microbubble looks like, okay? So this is gas filled within a protein shell, okay? Or a lipid shell, okay? So this is without contrast, this is with contrast. So you can see that the tissue absorbs more of these microbubbles, and we're able to see the tissue opposed to that structure that did not absorb the contrast agent, right? Okay, and here we see the contrast agent again that is absorbed by the structure, okay, by the kidney. You see? And this structure here did not absorb it, which means that it is not normal tissue. Okay? See, it's not normal tissue, this is not normal tissue. Okay? And it is identified because there is microbubbles that are absorbed by the tissue.
For ultrasound is really digestive, right? Okay, they'll drink the liquid.
To be honest with you, I've never seen contrast agents used in ultrasound. So like I mentioned, it can be ingested or it can be injected. Which one of the two is used more frequently? I have no idea. Okay, so continuing on with contrast harmonics. As a pulse interacts with contrast agents, stronger harmonics are created. Okay, stronger harmonics are created because there is more irregular behavior from the microbubbles than there is of regular cells in the tissue. Okay, contrast harmonics are created because microbubbles act in a nonlinear manner when struck by sound waves. Contrast harmonics are created during reflection as energy is converted from the fundamental frequency to the harmonic frequency. Okay, so what's the benefit of the harmonics being created during the reflection?
The intensity.
What happens when sound travels? It
Attenuates.
attenuates. Okay, so we're canceling the attenuation from the traveling, and it's just going from the reflector back to the probe. So there's less attenuation. Significantly less attenuation than tissue harmonics. Okay, because tissue harmonics still have to travel through the tissue, which attenuates, and reflect, travel back, which attenuates. These are created just on the return, okay, just on the reflection. Is there any questions on this? Are you sure? Okay, so what are the three types of harmonics that we went over today? Yes. Okay, pulse inversion, power modulation, and contrast harmonics. Okay, what is the difference between the three? Pulse inversion is opposite pulses.
Power modulation is 2 times the fundamental frequencies, and then during reflection, the weaker one is 2
2 turns again, so it cancels out, and you're left with the harmonics.
Okay.
And then contrast is during reflection,
During reflection caused by what?
the gas motor.
The nonlinear behavior of gas bubbles. And which other harmonics are we missing? Tissue harmonics. Okay, so which one out of all of the methods do you think is the best for harmonics? Why? Okay, so we just, alright, so we just talked about it, right? Tissue harmonics, travel,
Oh, no,
contrast, right? Because the contrast harmonics happen upon reflection. Pulse inversion, power modulation, and tissue harmonics all happen through transmission. So there's attenuation from transmission and reflection. Okay, contrast is just reflection. Is there any questions?
Not yet.
Yeah? Okay, that's gonna be it for today.